Now that we understand speed, velocity, and acceleration, we can start talking about Newton's three laws of motion. Now, really quick, something I want to point out. Last time we talked about Kepler's laws of planetary motion, and of course there are three of them. Now we're talking about Newton's laws of motion, and there are three of them. So be careful, make sure you know which set of three laws we're talking about. So again, this is Newton's three laws of motion. Newton's first law states an object moves at constant velocity if there is no net force acting upon it. So we've got some things we have to unpack here. So an object moves at constant velocity. What was velocity? Velocity is speed and direction. So a constant velocity means a constant speed and a constant direction. So an object is going to move in a straight line, constant direction, at the same speed until it is acted upon by a net force. Okay, so it has constant velocity if there is no net force. Okay, so we understand what constant velocity is, but we don't really understand force. Okay, so our simple definition for force, what we're going to start with is a push or a pull. A force is simply a push or a pull. Now, a force is the way that we're going to change an object's momentum. So now we have another word we have to define. Momentum, the idea, the concept, is how difficult it is to change an object's motion. Okay, so an object in motion wants to continue in motion. Now, the math of momentum is the object's mass times its velocity. Okay, so remember, velocity has direction, which means momentum also has direction. So momentum is the mass times the velocity, and the idea of it is how difficult it's going to be to change that object's motion. If an object has a greater momentum, you're going to have to supply a greater force to see the object's motion change. So some examples of dealing with momentum, we can use a fly and a train. If both the fly and the train are moving at 30 miles per hour, then we know they have the same speed, and if they're going in the same direction, they'll have the same velocity. However, which one is going to have a greater momentum? I hope you say the train. The train has way more mass than a fly does, and therefore the train is going to have a much greater momentum. Okay, now, if you remember, we said a greater momentum is going to require a greater force to lead to an acceleration. So, think about a fly. Okay, hopefully you've had the experience of hitting a fly out of the air, or something similar. Because the fly has a very little momentum, when you actually hit it, it's very easy to change its momentum. Now, the hard part is actually hitting the fly, making contact with it, but if you do, it's really easy to get it to change its motion, meaning it has a very small momentum. Okay, so just smack and the fly changes direction. However, imagine doing the exact same motion with a train, walking up and just smacking a train that's traveling at 30 miles per hour. Are you slapping the train going to get it to change its motion? No, you're not, because that's a very small force compared to the very large momentum of the train. So a train's momentum is a lot greater, meaning it's going to be much harder to get it to change its motion. Now, things that we should point out. Just because there are forces acting on an object does not mean we're going to get an acceleration or a change of the object's momentum. So, as an example, we have this person standing on a bathroom scale. Now, we have different forces acting on this person. Okay, so as we look at the forces acting on the person, we know that they're standing on the earth, so we have gravity, which is pulling down. Now, they're not just falling, sinking into the earth, because in this case, they have a bathroom scale that is going to be pushing up on them. So we have gravity pulling down, and we have the what's sometimes referred to as the normal force, or the support force pushing up on this person. Now, if these two forces are acting on the same object, in this case the person, and they have the same amount of force, but in opposite directions, then we say that they cancel out, or in other words, they balance each other. If you have two forces that are opposite in direction, that means that you're going to subtract if you're going to actually work out the math, and that means that the net force is going to be 0. And if there is no net force, then we learned from the first law there will be no acceleration. It will continue at a constant velocity. So right now, the way that we are using net means total. Another place that we use net in the same way is actually on a paycheck or a pay stub. So if you've recently looked at your pay stub, up at the top they have your gross pay. The gross is the total amount that your employer says you have earned. So working for this many hours at this much per hour, here's your gross. Now, as you go down the pay stub, you're going to see different spots where different amounts are getting taken out. So for example, tax, and then Social Security, and maybe insurance if that's something your employer does. Okay, so all of these things are getting taken out from your overall, your gross pay, and down at the bottom is the net pay. The net pay is what's actually given to you in check form or put into your bank account or however it is that your employer pays you. The net is the total. It's what's left over after everything has been taken out. This is the same idea as net force. What is the remaining force once we've subtracted out all of the opposing forces? Okay, so the net force. And it's the net force that is going to lead to accelerations. Okay, so the first law states that an object will continue at constant velocity if there is no net force acting on it. So as long as there's no net force, we have a constant velocity, meaning there is no acceleration. Now from this, we can actually make a corollary, which means something else that we can arrive to, something else we can conclude based off of just that statement. The corollary is that if there is a net force, then there must be an acceleration. So if there's no net force, we have no acceleration. If there is a net force, there will be an acceleration. And that idea leads us to Newton's second law. Okay, so Newton's second law tells us how much force and how much acceleration. So I've tried to figure out lots of ways of writing this without resorting to math, but really, in my opinion, the best way to understand this is to actually look at the math. So Newton's second law states that the net force is equal to the mass times the acceleration. So if we know the amount of the net force, the total force after including all of the other forces, and we know the object's mass, then we can determine the acceleration. This is sometimes written F equals ma. Force equals mass times acceleration. So something that we can conclude from this, something that we see from F equals ma, is that more force means more acceleration. If we have a greater net force, we're going to have a greater acceleration. And so for me, the way that I kind of think about this is in dealing with having to push a car. Hopefully you haven't ever had to have that experience, but maybe you have. So imagine that you have a big truck that you have to push out. As you're pushing on it, just you by yourself isn't going to really make it change its motion all that much, get it moving. However, if you call up a couple of friends, then a whole bunch of you pushing together can get it to move. In this case, because you have more people pushing on it, then you're going to have more force, and that's going to lead to more acceleration. It is going to be easier for you, and it's going to actually get the big truck moving. Something else we see from this is more mass leads to less acceleration. If you're pushing on an object with a greater mass, you end up with less acceleration. Okay, again, going back to pushing a car. Imagine a small compact car versus a big truck. The small compact car has a lot less mass than the big truck does. And because of that, you by yourself can probably actually get the small car moving at a decent speed. Not anything like several miles an hour, but a couple miles an hour, so it's actually moving by yourself. However, if you're trying to push a big, heavy truck, it has way more mass, so it has a lot less acceleration. You're going to have to push a lot longer for it to actually get moving. So this is Newton's second law. More force leads to more acceleration. More mass means we get less acceleration. Now, something to notice with Newton's second law, the net force is equal to mass times acceleration. Mass does not worry about direction. You have the same amount of mass no matter what direction you're looking. However, we mentioned previously that acceleration does have direction. So the direction of the net force is always going to be the same as the direction of the acceleration. Now to Newton's third law. Newton's third law states that whenever one body exerts a force on a second body, the second body exerts an equal force in the same direction on the first body. I realize that is super wordy and kind of confusing. Now, this is sometimes stated, for every action, there is an equal and opposite reaction. Now, if that helps you remember what's going on, fine, go ahead and use it. However, I kind of have a problem with this. The problem I have is the word reaction. This sounds like there is a choice involved, and that's not the case. The forces arise equally at the same time, regardless of what anybody decides or chooses to do. Okay, so for example, the man is pushing down on the floor, therefore the floor is pushing back up on the man. The floor has no choice. The man has no choice. The forces just are. So as long as you understand that caveat, go ahead and use this other statement if it helps make sense. All right, so let's unpack what's going on. Whenever one body exerts a force on a second body, in other words, we're now starting to deal with interactions between two objects. So the first law, Newton's first law, and the second law actually only deal with a single object and its own motion. Okay, so the first law states that it will continue with constant velocity if there's no net force. And the corollary is that if there is a net force, then it will not continue with constant velocity. We will see an acceleration. Then the second law says for that one object, given this amount of force and the object's mass, we can expect this amount of acceleration. We're only looking at a single object. With the third law, we're now looking at what happens as two objects interact. Okay, so we have one object, one body, and we have a second body. When those two objects interact in some way, the first object is going to be pushing or applying a force on the second object. Then, the second object, whatever it is going to apply an equal amount of force, but in the opposite direction on the second object. So, for example, we have this man who is pushing down on the floor. So we're looking at two objects, the man and the floor. Those are the only two objects we're interested in with this interaction. Just the man and just the floor. We can ignore everything else. So let's say that the man is pushing down on the floor with 150 pounds of force. Okay, so he is pushing down with 150 pounds. What the third law then states is that the second body, in this case the floor, has to be pushing with the same amount of force, the same 150 pounds, but now in the opposite direction and on the man. So the man pushes down on the floor with 150 pounds of force, therefore the floor is pushing up on the man with 150 pounds of force. Okay, I realize that thinking in these terms gets a little bit confusing. What may help is identifying what are the two things that we're looking at. In this case, we're looking at the man and the floor. The man pushes down on the floor pushes up on the man. Again, notice opposite directions. Okay, so it is an equal amount of force, but in the opposite direction and on the other object. The man pushes down on the floor with 150 pounds of force. Therefore, the floor pushes up, opposite direction, on the man with an equal amount of force, 150 pounds of force. I hope that works. Again, it's a little bit hard to wrap your head around, but hopefully we'll make it through. All right, here is our second clicker question. If an object accelerates, this means A, all forces on the object are balanced. B, there are no forces acting on the object. C, there's an unbalanced force in the direction of the acceleration, or D, there's an unbalanced force opposite the direction of acceleration. Go ahead and think about it, and we'll discuss in just a bit. All right, if there's an object that accelerates, then we know that there has to be a net force. So the first A states all forces on the object are balanced. If all of the forces are balanced, that means that for every push right, there's an equal amount of force pushing left, which means they cancel out, which means there would be no net force. So A does not work. B, there are no forces at all. Well, if there's no forces at all, the net force is 0, and if there's no net force, there's no acceleration. So that one doesn't work out. So looking at C and D, C states there's an unbalanced force. D also states there's an unbalanced force. So far, so good. However, C states in the same direction as the acceleration, but D states their force is in the opposite direction of acceleration. Force and acceleration are always in the same direction, or rather I should state the net force is always in the same direction as the acceleration. So the correct answer is C.